Welcome back to the Deep Dive. Today we are taking a deep dive into the absolute foundational piece of networking, the Cisco router.
Yeah.
You handed us a great set of materials covering, well, everything from the silicon itself to the critical CLI commands you need to make that box actually move packets.
Right.
Our mission right now is to sort of skip the dense documentation and just pull out the most essential nuggets of knowledge, the exact steps and concepts you need to get from just looking at a router to confidently configuring one.
That's absolutely right. I mean, routers are the core of the network layer. They're forward IP packets from end to end.
And it can be overwhelming.
Oh, completely. It's easy to feel, swamped. The Cisco documentation has literally thousands of commands.
Thousands.
But we're going to be laser focused on the critical few. We just need to know how the brain, the OS works, how the body, the hardware is changing, and most importantly, the two simple steps that turn an interface from an expensive paperweight into a live, functioning Layer 3 link.
Okay, let's unpack this starting with the brain of the device, the operating system. For decades, the standard was Cisco's IOS. But your sources immediately point to a big evolution. IOS XE. This isn't just a version update, is it?
No, it's a fundamental architectural shift. IOS EXEC was developed back in the 2000s to really modernize the software base.
Yeah.
And network engineers love it because the command line interface, the CLI, is pretty much identical to classic iOS.
So the learning curve is flat.
Exactly. But the internal benefits are, well, they're revolutionary, especially for enterprises.
And the key takeaway here isn't just it's new, it's that XE guarantees this massive improvement in network continuity and uptime. Where does that really show up?
It's the zero downtime mentality. Think about a major operation like an OS upgrade.
Right.
Traditional iOS makes you do a full system reboot. The whole thing goes down.
Which is downtime. Planned, but still downtime.
Right. iOS XE, because of its architecture, it can isolate services. So this means the core routing process can just keep forwarding frames and packets. Your network stays up while the upgrade happens in the background.
Oh.
That level of resilience and, automation capability is why XE has become the standard in the enterprise.
That is a subtle but massive difference, especially when you start calculating the cost of that planned downtime.
Yeah.
Okay, let's move from the software to the actual box itself, because even the hardware's identity is shifting.
Right.
We spent years talking about the integrated services routers, or ISRs.
Yes, ISRs,
Yeah.
that product family introduced around the mid-2000s was all about multifunctionality. They weren't just routers.
There were more than that.
There were routers plus switches plus VoIP processors plus security services all in one box.
Perfect for a branch office.
Exactly. They were ideal for branches that needed everything consolidated. The name itself, Integrated Services Router, tells you exactly what it's for.
But now, post-2020, we see this new branding push. The Cisco Catalyst Edge platform, specifically the 8000 series. And this is where it gets really interesting, because Cisco seems to be deliberately avoiding the word router in the name.
It's fascinating, right? It's an evolution of language. Cisco is moving away from describing a product by its function, a router, and instead describing it by its purpose.
A platform.
A platform, yeah. They want to emphasize that the device is a foundation where you can run all these different network services. Routing is just one of them.
And for anyone who's been around for a while, the term catalyst was, it was historically for switches, for layer 2 devices. Now they're putting it on these high-end layer 3 devices. It feels like they are intentionally blurring the lines.
Oh, they absolutely are. If you see a Catalyst 8000 series device, you should definitely understand that while it might switch some traffic, its primary role is routing. It's a modern, high-end, dedicated layer 3 platform.
So regardless of what we call it, an ISR or a Catalyst Edge platform, the installation context matters a lot. Your sources draw a really sharp contrast between setting up a big enterprise environment versus a small home office. The Soho model.
Oh, the complexity difference is just night and day. In an enterprise setting, you're all about modularity, separation of duties.
So you have dedicated boxes for everything.
You typically have dedicated routers, separate LAN switches, separate wireless access points. And that means the cabling for your wide area network, your WAN links, can get pretty detailed.
Like the classic setup for older serial LAN links. You often had to deal with a channel service unit, data service unit, a CSU/DSU.
Exactly, that box that sat between the router and the ISP's connection. And the ISP often uses a proprietary connector, like the RJ48.
Which looks just like an Ethernet port.
Looks identical to an RJ45, but it's wired completely differently. And then moving to modern Ethernet WAN ports, flexibility is everything. That's why you see enterprise ports using those small form pluggable modules, the SFPs.
Okay, and that's essential
Because it lets the engineer choose the specific fiber Ethernet standard they need for the WAN service. If the ISP changes fiber types, you just swap the little SFP module, not the whole router card.
And one small but practical detail our sources highlighted, enterprise Cisco routers usually have a physical on-off switch. You almost never see that on a Cisco switch, which just powers on when you plug it in.
Right. Now contrast all of that meticulous modular enterprise setup with the SOHO environment. The SOHO device is all about convenience and cost. It's almost always a multifunction box.
All in one.
Router, switch, firewall, VPN, wireless access point, all in one chassis.
And for the WAN connectivity, the complexity just plummets.
Yeah.
They're relying pretty much entirely on standard broadband and VPNs for secure access.
The perfect real-world example is connecting a SOHO device to a cable modem. The cable modem handles the coax from the ISP.
And then a normal Ethernet cable connects the modem to the router's WAN port.
And that's it. It's simple, it's integrated, it's designed to be deployed instantly. The design philosophy is the total opposite of the enterprise model.
So we've got the box powered up, cables are plugged in. Now for the moment of truth, making it actually route packets. This takes us into the CLI, the essential configuration. We know it looks the same as a switch, same mode, same password configs, but what's the single biggest conceptual difference we have to account for?
It's how the interface is treated. A switch, it treats its physical interfaces as layer 2 interfaces. It's all about forwarding frames based on ME addresses.
Okay.
A router, however, treats its physical interfaces as layer 3, or routed interfaces.
Meaning the router expects to process the whole communication, it strips off the layer 2 frame, looks at the layer 3 IP packet inside, and then runs its routing brain to figure out the best path forward.
Precisely. And for a router to do this essential job, you have to overcome 2 specific defaults that Cisco sets to prevent a router from accidentally routing traffic before you're ready.
Okay, what are they?
First, the interfaces are typically disabled. They're in the shutdown state.
Right.
And second, they have no IP address configured.
Why do they default to shutdown? Is that just a safety feature?
It's protection and process control, really. A major network change should be deliberate. If you add a new interface card to a live router, you don't want it just randomly coming up and messing with your routing topology until you, the engineer, have explicitly configured its IP address and checked everything.
That makes perfect sense. So we need only two core steps to enable an interface for basic IPv4 routing. What are those commands?
Step 1. You have to assign the interface a unique IP address and subnet mask. This is done with the interface subcommand app address, then the address and the mask.
For instance, IP address 192.168.011.255.255.255
Exactly. That defines the network that's connected to that port.
And step 2.
Step 2 is enabling the port. You just reverse that default shutdown state using the interface subcommand no shutdown.
So IP address and no shutdown.
Those 2 commands, they're the critical configuration difference between a router interface and a switch interface. You get those right, and you're routing.
Okay, once those commands are in, we need to verify. What are the essential show commands that give us that quick health check?
The quickest check, and I would argue the most important, is show IP interface brief.
Why that one?
It's superb because it gives you that perfect snapshot. 1 line per interface lists the IP address and, critically, the status codes.
Okay.
For a bit more detail, you can use show protocols, which adds the mask info. And then for the full information download, including the description you set, you use show interfaces and then the specific interface.
Those status codes are a real indicator of health, and they are, I think, the #1 spot for troubleshooting confusion. Every interface has 2 codes, both have to be up. What are those 2 codes actually measuring?
This is where we break down the OSI model in a really practical way. The first status code, the line status, that's strictly layer 1, the physical layer.
So is the physical signal there? Is the cable plugged in? Is the device on the other end powered on?
Exactly. The second status code, the protocol status, that refers generally to layer 2, the data link protocol. Is the device talking correctly to its neighbor?
And there's a hard and fast rule here, isn't there? If layer 1 is broken, layer 2 doesn't even matter.
Absolutely. If the line status is down, the protocol status is always down. You can't negotiate a layer 2 protocol if you don't even have a physical connection.
Let's break down the 3 common scenarios you'll see, because this tells you exactly where to look. Scenario 1, I see administratively down.
That is the easiest to fix, assuming it's not on purpose. That tells you the line status is down because you, the engineer, explicitly configured the shutdown command on that interface. It's a deliberate choice, not a cabling error.
Okay, got it. Scenario 2, down. The interface isn't shut down, but the status is still down.
Now you have a physical problem. Layer 1 is failing. This could be a missing cable, a bad fiber connection.
Or the device on the other end is just turned off.
Or the port on the other side is shut down. Or maybe even a clocking mismatch on an old serial link. It's time to check the physical layer.
And the final one, and this is often the most frustrating for a beginner, up-down. Layer 1 is good, the cable is in, lights are on, but Layer 2 is failing.
That is almost universally a data link configuration mismatch. On a dedicated serial link, for example, one router might default to using HDLC high-level data link control.
And the other side is set for PPT.
Right, the point-to-point protocol. They're trying to speak different languages at Layer 2, so the protocol status drops. The only fix is to make sure they're both configured to use the same Layer 2 framing protocol.
Understanding those two status codes is, it's a shortcut to half of network troubleshooting.
Let's stay in the configuration weeds for a second and talk about Ethernet speed and duplex, because this is where that OS nuance really comes back into play.
Oh, it is a constant source of error. The general recommendation is strict. Either use auto-negotiation on both ends,
or manually set both the speed and the duplex on both ends.
Exactly. You absolutely have to avoid mixing manual settings on one side and auto on the other. You're just asking for intermittent failures and horrible performance because of a duplex mismatch. That makes perfect sense. But if you're trying to manually configure a port, there's a subtle but massive gotcha depending on whether you're using traditional iOS or the newer iOS.
This is a perfect point for the learner. On traditional iOS routers, just like their switches, if you set the speed and duplex values manually, that automatically implicitly disables auto-negotiation.
So you just type speed 100 and duplex full, and the router just figures it out.
Right. But if you try that exact same command sequence on an iOS XE router, what happens?
It doesn't work.
It rejects it. iOS XE is more rigorous. It defaults to assuming you want auto-negotiation on. If you try to set the speed first, the router will throw an error message. It won't let you set a fixed speed while auto-negotiation is running.
So what's the fix?
You have to explicitly disable auto-negotiation first. You use the no negotiation auto command. Then you can set your specific speed and duplex. It's a critical difference that stops a lot of engineers cold when they're migrating platforms.
Wow, that is a subtle requirement that could easily derail a whole configuration session. How do we check which mode we're in on that newer platform?
If you run show interfaces on an iOS XE box, you'll see explicit detail. It will literally say link type is auto if it negotiated, or link type is force up if you configured it manually. It takes all the guesswork out of it.
We've covered modern OCs, hardware evolution, the 2 key enablement steps, and the status codes. Before we wrap up, there's one unique physical port on most Cisco routers that stands out as a kind of dedicated lifeline: the auxiliary, or O, port.
Ah, the O port. It's a practical anomaly. It's unique to most Cisco routers. You won't find it on their switches. And its whole function is for remote, out-of-band management. We're talking true disaster recovery here.
So the scenario is the network is completely down. Maybe there's a catastrophic config error that locks you out of all the normal IP management interfaces.
Exactly. When the network itself is broken, the O port lets an engineer connect through an external analog modem, which connects to a standard phone line. The engineer can then dial in from home or wherever and get to the command line over the phone line.
It's basically a panic button, a management channel that is completely separate from all the production network traffic.
That's its utility. You configure access using the line O0 configuration mode, just like you would the console line. It provides a secure, dedicated channel for fixing things when the primary network interfaces are dead. It's insurance against total connectivity loss.
This has been a tremendously efficient deep dive. We started by defining the resilient architecture of iOS XE and the significance of Cisco blurring the lines by using that Catalyst branding for their new router platforms.
Right.
We contrasted the complexity of enterprise installations with their dedication to modularity against the simplicity of the integrated SO box.
And most critically, we distilled the configuration process down to the absolute essentials, defining the interface as layer 3 with an IP address and then explicitly bringing it up with no shutdown.
And now you have a working knowledge of those critical status codes line and protocol, which tell you exactly where the problem is.
Whether it's config, layer 1, or a layer 2 protocol mismatch.
So what does this all mean for the future of network design? We talked about Cisco creating these integrated platforms that handle Layer 2 switching, Layer 3 routing, wireless, security, all in one box.
Right.
If every device is becoming this multi-talented platform, maybe the lines will only continue to blur.
Then here is a provocative thought for you to chew on as you continue to learn. If modern network devices are becoming so integrated and versatile, capable of handling everything from layer 2 switching to security services, what is the most enduring and distinct purpose of a dedicated router in a contemporary network design? What core function, fundamentally, can't be absorbed or just offloaded to a high-end switch or some other service platform? Think about the essential job of a router that just can't be eliminated.
That is a great question that makes you rethink the very definition of the device itself. Thank you for joining us for the deep dive. Keep digging into your sources, and we'll see you next time.